So I have this EPCERT grant. I'm the guy with the EPCERT grant to prove Fermat's last theorem. And as has just been confessed, I spoke about it last year, but they asked me to come and give you an update. And so, unsurprisingly, given that I spoke about it last year, I'm mostly going to talk about what happened since I last spoke. Although I will give some initial background chat just for those that weren't here last year. But the things that really, I've learned some quite different things, and I had to decide what to talk about. So one thing I'll talk about is what it actually means to run a very large formalizing project in practice, because that was something I really didn't know at all last year. Like, all I knew last year was this is what I was doing, but I didn't actually know how to do it. So I've learned something about that. So I'll say something about how to run a large form. I thought that was appropriate for the seminar, and then I'll also talk something about. I'll tell you about some new mathematics that somehow come out of the formalization process. And I was also, I guessed Larry would come, so I was going to have a section on errors, but I did a run through this morning. It was too long, so we've lost the section on errors, I'm afraid, Larry. Yeah, I mean, mistakes we found in the literature when formalizing. Because people were just like, well, you're going to find mistakes. I was like, of course I'm not going to find mistakes. So anyway, Fermat's last theorem is this statement here, some random statement about positive integers. And the only unnatural condition about it is this n is at least 3, but you have to have, it's been known for 3,700 years that you have to have n at least 3, because the Babylonians are really into their multiples of 60. So this is the first entry on this Plimpton, whatever it's called, some ancient clay tablet that survived 3,700 years. So you need n at least 3, but sum of 2 squares can be a square, but sum of 2 cubes can't be a cube. So the statement, Fermat was a 17th century French mathematician, but the statement of the claim is comprehensible, for millennia. And so Diophantus was the kind of person that was interested in polynomial equations and solved many of them and wrote a book about these things, like searching for solutions to polynomial equations in whole numbers and in rations. So Fermat had a copy of Diophantus's book, and he wrote in the margin of his copy, when Diophantus was talking about x squared add y squared is z squared, Fermat wrote in the margin that he discovered a marvelous proof that you couldn't have sum of 2 cubes being a cube or any higher powers. And he said that the margin was too small to contain it. And for all we know, he wrote this many years before he died. It wasn't like he died the next day and the proof was lost. There's evidence that he wrote this several years before he died, and probably the next day just realized that it was wrong, but then never went back and deleted the claim. So this marginal comment was discovered by one of his children after Fermat had died. So we don't really know. So John Coates told me, I think there's like a copy in Emmanuel Library, or it's seen a copy or something. This book, when you look at the book, has got very big margins. It's quite, maybe all books look like that in those days. I don't know. But so there's the statement. And to state the result, you only need positive integers. But what's kind of interesting is that the proof of the result uses much more complicated things. And we don't really know if that's necessary, if there's a proof that just stays in the positive integers. I mean, maybe logicians will tell me that actually we do know. But there might not be a proof. There might not be a sort of a comprehensible proof that only uses positive integers. So all known proofs use many more more complicated mathematical objects like He plays a key role in the proof, and negative numbers as well, and all these sort of fancy things, elliptic curves and modular forms, and buzzwords play a. So things that Fermat certainly didn't know the first thing about. So certainly Fermat, did he have a proof? It's certainly clear that he didn't have the proof that we now know. So the claim was made, we don't really know when, approximately 1637. And the big news when I was a PhD student in 1993, was the proof was announced by Andrew Wells just up the road, just next door in the Newton Institute. And it was really big news. It's one of the biggest mathematical stories of the century, basically. Proof was on the front page of the New York Times. So the strategy was completely new. It was an innovative paper that did lots of things, but it turned out that part of it was wrong. But a year later, it had been fixed by my advisor and Wiles working with so Wiles was in Princeton, Taylor was in Cambridge. When it was clear that the proof was erroneous, Taylor just cleared off to Princeton to fix it, leaving me without an advisor. But there was no Zoom calls then, but email did exist, and academics had email, so at least I could email. So that's the history of the proof, and then there's this, why formalize it? Well, one daft reason to formalize it is this guy, Frank B. Dyke, has this list of 100 mathematical formalization challenges, which existed in like paper form since the 90s. He maintains some website which keeps track of these 100 challenges, and some of them are very straightforward, like, you know, sort of proving Pythagoras' theorem or whatever. But around when I entered the area, about 80 had been formalized, but now formalization of mathematics has become a thing, and so some of the non-trivial ones have been formalized now. And in fact, all but one have been formed. For some reason, Fermat's last theorem made it onto the list, probably because it was proved at pretty much the same time that the list was initially compiled. It's orders of magnitude harder than essentially all of the other problems on the list. So it's a silly list in some sense, but it is true that of this list, 99 of the theorems have now been formalized, and this is the last one. And as I say, I got an EPSA grant just over a year ago to work on a lean formalization of the proof, which started last October. So last comment about background before I get on to things I've learned and things I want to tell you. How big is the project? Just to give people an idea. While this paper was 100 pages, it's 110. But it doesn't do, barely mentions positive integers. It's not really about positive integers at all, because what happened was in 1990 or 1989, Ken Rivett finished the proof that Fermat's last theorem was a consequence of some fancy conjecture in the Langlands program called various things, but at the time it was called the Taniyama-Wei conjecture, and then the Shimura-Taniyama-Wei conjecture, and now some people call it the Shimura-Taniyama conjecture. So this is politics, not mathematics. It's all the same statement, but it's some fancy statement about elliptic curves and modular forms, which is a consequence of the Langlands program. And this is what Wiles did. So it's all elliptic curves and modular forms and Galois representations, and then it's just a remark at the end of the introduction that, as a consequence, they've now proved Fermat's last theorem. So there's not really, there's no manipulation of integers in the paper, and 100 pages doesn't sound too bad, right? Because for example, well over a decade ago, Georges Gontier formalized the Fike-Thompson proof of the odd order theorem in group theory, and that was 2 mathematical textbooks which totaled about 300 pages. But the big problem is that the 100 pages is not remotely self-contained. It's got 80 odd references, whereas these 300 pages that Gontier and his team formalized is essentially self-contained, other than like standard undergraduate and beginning graduate level. So somehow the full proof is much longer than 100 pages. So the paper is, as I say, fancy, technical, modern stuff. In some area of mathematics, this is like algebra, number theory stuff, arithmetic geometry, but then the references use other kinds of geometry, differential geometry, which is calculus, and harmonic analysis, that's also calculus. So you're using the discrete and the continuous and lots of things. The proof is really the proof uses lots of things from lots of different areas of math, which is one of the reasons I was interested in formalizing. So I make this claim that it's impossible to find one human that knows all the details, and I sometimes make that claim, and then that sometimes annoys people because they claim that they do know all the details. And so maybe, and what I've realized is that this vague statement, a lot depends on what you really mean by the word "know." somehow.
Wiles is still alive?
No, I asked Wiles, but they, in the 25-year anniversary of the proof of the theorem in the Newton Institute, Andrew gave a talk, it was all recorded, and at the end of it, Tony Scholl said, "Are there any questions?" And I stuck my hand up and asked him if he understood the proof of the Langland tunnel theorem, which is one of the theorems which is used in Wiles's proof. And he didn't say yes. He gave quite a long-winded answer, which is available on the Isaac Newton Institute website, so you can listen to what he said. But he didn't say yes. Anyway, so it depends what you, and then, as I say, you might find people that claim they know all the details, and then the part of the talk I'm not going to give, like when you find a mistake in the literature, it's like, well, you didn't know that detail, then did you? Because like that detail turned out not to be correct. So it depends on what you mean by no. But basically, the point of this beginning bit is that the proof is broad, uses lots of areas of mathematics, and it's also deep. It uses quite complicated mathematical objects, and it's also very long, perhaps as a consequence of it being broad. So maybe it's a couple of thousand pages if you write it out in full. And I'm certainly not claiming I know. So what am I doing? I'm certainly not claiming I know all the argument, because I'm not very good at analysis, is the bottom line. Wiles's proof uses a lot of algebra, but there's various black box inputs from harmonic analysis. But I'm relying on the fact, the point is, I certainly know enough harmonic analysis to understand the statements of the theorems that Wiles uses, but not enough. I mean, I could sit and learn and plow through the proofs. I'm sure that, you know, I just don't want, I don't like analysis. This is the bottom line. I don't want to read those proofs. But I know enough to understand the statements, and I know enough to formalize the statements. And that's the nature of mathematics. Sometimes you can have very small statements that have very big proofs. So it's sort of not inconsistent. I can formalize the statements. And then not formalize the proofs. So in the remaining, what did I actually tell EPSEC I was going to do? The idea is, I said that I was going to, you know, formalize the results of Wiles's paper and not the references. That's what I claimed I would do. And this is because I was giving the talk, I was sort of motivated to actually try to figure out what that would actually look like. And so yesterday, so this link didn't work yesterday, but I think I've merged it since. So I've got this is, you know, me explaining what's going on. There's going to be, I'm going to prove the theorem modulo some formalized assumptions, and I've probably got one example. There you go. I've done one assumption. This is this is some lean code. This is some analytic number theory. So I've got a doc string talking about the mathematics and explaining why I need the mathematics. And there's the reference. This is a precise reference to a paper that was written in 1977, and this theorem is proved in that paper. And I've added it as an axiom. And so at the end of the day, my proof, so sorry means I'm skipping the proof, my axiom means I'm cheating. So at the end of it, the idea is I'll have a proof of Fermat's last theorem, and the proof will only use lean standard axioms, and also these five or six at least extra results, and the rule is all of the extra results have to be known in the 1980s. That's and now I don't know how max work. Oh, I can do this. I do know how max work. You do that, and then you do that. There you go. 3 fingers up. So that's the rule. So everything has to be pre-1990. So then the proof is I've reduced Fermat's last theorem from the 90s to the 80s. That's where we're going. And, you know, I'm going to work back. That's because it's much more fun. If we started at the bottom and just worked up, then after 5 years, I'd still be typing in graduate courses, basically. And I don't want to do that. I want to do the fun part. You know, the part that sort of made my career, because my PhD was in this area. You see, I want to do the part which I sort of known for decades and you know, my area of mathematics. So that's the plan. So there we go. And so now one slide on where we are, and then I'll talk about the things I've learned. So what does Wiles do in his paper? He proves an R equals T theorem. This is a big technical innovation. And the abstract R equals T theorem, when you abstract everything away, it's just a statement in commutative algebra. And that's done. done by Andrew Yang, one of my PhD students. But I need to apply it to a ring R and a ring T, and we've not defined those rings R and T yet. So the theory is sort of, we can't use it at the minute, but we're well on the way to defining R and T. R has got a fair bit of work to do, but T, I've done all the machinery to write down the elements of T. And if I had like 5 hours, I could just sit down and do T. So T is very close. There's been a huge amount of work to get to it, but we're really not that far away. I'm giving another talk on the same topic in a month's time at this big proof conference. And I will almost certainly have, the big reveal will be that I've defined T. And if I work really hard, maybe we'll get R. So even if we do define R and T, so let's say that's going to happen, because you can imagine in a month that might have happened. Then we're going to have a theorem of the form, if a bunch of hypotheses about this particular ring R and this particular ring T are true, then these rings are equal. Well, isomorphic. That's what the abstract algebra says. Under certain hypotheses, these rings are equal. So that's what we'll get. You can imagine having that in a month's time. But the problem is these hypotheses, some of them will be, some of them are, to prove them are hundreds of pages. And then, of course, there's also the problem that you've got to get from what Wiles did, R equals T, to all the standard machinery that the experts knew by the 90s implies Fermat substitute. So in some, we're sort of stuck down a marker sort of in the middle of the proof. And so, there's some bit that we actually know quite a lot about in the middle. So now instead of having to prove one big theorem, we've got to prove 2 theorems that are half the size. So that's where we'll be. So the project's been run using Blueprint stuff. I was not sure whether I would have internet, but I think I've got internet. So that's a random screenshot of a random project, Terry Tao's polynomial Freiman-Ruger project that's run using this Blueprint software. But we don't need to worry about the screenshot, because I'm pretty sure that I'll be able to actually show you some real blueprints. So this Blueprint software it's sort of lean and LaTeX joined together, and it gives you some sort of graphical realization of how well you're doing. This project is essentially done. The dark green boxes mean this theorem is proved, and as are all of the theorems that it relies on. And the blue things mean this theorem is stated but not proved. So it gives you some kind of idea about where you are. And I thought one thing that might be sort of helpful was to compare this project, the Fermat style. I'm not the only person doing a big lean project, right? There's now an industry of people doing big lean projects, and Floris von Dorn is in Bonn running another project called the Carlson project. So if I there we go, and that's his blueprints. And he's, as you can see, so you can just see immediately that they're sort of quite a long way towards finishing it. So there's very few white blobs. The white blobs haven't even stated it yet. Proved. Green means stated and proved, but some of the prerequisites aren't. Like that's green because there's a blue thing going into it. This theorem is proved, but it relies on this theorem which isn't. So that's the sort of the logic of the. So you can see it's all very, very clear. You could just look at it and instantly know they're like 70% of the way through the project. That's kind of nice. Oh, and I can't do clicking because now I'm going to get back to. There we go. So this project there that I just showed you, the Carlson project, is an ongoing project to formalize a theorem in harmonic analysis. And the way it worked, so the original paper proof of this theorem was 30 pages. And so paper proofs are no good for us, right? Because they just say, the other cases are similar, or the proof is well known. And so the point is, Lean doesn't buy that. So they took the original 30-page paper, and before they even announced the formalization, they'd written a 150-page blueprint. So that containing the same material, but now all of the, and the rest is easy, has now been sort of removed and replaced with far more detailed arguments. So the 30 pages became about 120 pages proving the big theorem, but then there's sort of 30 pages of background and corollaries and things that weren't in the paper at all. So the expansion factor was about 4. And so, you know, if the expansion factor, so I've got the same issues, right? I've got 110 pages and maybe the expansion factor is 4. So maybe I'm supposed to write sort of 450 pages or something. And now the big problem with my project was that I'm having to write the LaTeX on the fly because everybody knew I was applying for this grant. And then when I got the grant, it was publicly announced on the EPSO website. And everybody knew I had the grant and I had no pages of LaTeX. But everyone was like, oh, now you've got to go, like, where's the project? Where's the repo? You know, there's a lot of sort of pressure on me from sort of academics and journalists and various people. So I just thought, okay, screw it. So here's the repo. There's nothing here. You know, there it is. Happy now. So there was no, now there is about 80 pages of LaTeX. And it's not, I didn't just start at the beginning and I'm working through. The way it works is you kind of choose a thing that you want to get done. And yeah, let's call that a sub-goal. So yeah, it's the thing you want to get done that maybe is, you know, sort of 2 or 3 pages of normal maths and aims for the sort of concrete goal. So you choose a sub-goal and then you call it a mini project to sell it to people. And then, first of all, I make sure I write the blueprint in my head, you know, or bits of paper to make sure that I actually do understand how to prove this sub-goal from the axioms of mathematics. And then I write the detailed LaTeX argument. And then once we have that, I then blueprintize it. I then write lean code that just contains the statements of the theorems and wire up the, you know, in the LaTeX, you say, oh, this LaTeX theorem corresponds to this lean theorem. So you have to sort of wire things up. That's how the blueprint works. You wire up the theorems to each other. That's the arrows in the blueprint graph, and then you wire up the LaTeX to the lean by just putting /lean in your LaTeX. You know, we've got a /lean thing in the LaTeX. And now we've got lots and lots of sorries, and then we want them solved. And we have a sort of pretty graph. And then I open issues on GitHub. Saying, you know, this, you know, we need to prove this theorem, the proof is here, we need to prove that theorem, the proof is there, we need to give this definition, you know, the details are here, you know, pointing to the blueprint. And then some of these issues, there's plenty of issues that aren't filling this sorry. You turn some of the issues that are sorries, you turn them into tasks, and there's a GitHub project page that I'll show you in a minute on the next slide. So we've got some GitHub project page, which is sort of keeping track of many, many, many small things. So when we're at the point where the tasks are there, I then advertise the tasks on the lean Zoolim. You know, there's a Fermat task theorem channel, and then there's discussion. You know, if somebody wants to actually do, if someone thinks, oh, I could do that, that'll take me an hour, they can claim a task. And so you do this on GitHub by typing the word claim in the issue. And then when a task gets claimed, then it's up to the user to make their pull request, and they make their pull request, and then a machine reads the pull request and checks that the code is. I only installed these last weekend for about, you know, for basically the duration of the project so far. I've been letting people push stuff which wouldn't satisfy Lean's maths library code requirements. Like lines could be over 100 characters long. Just random stupid things, or definitions might not have dot strings. But then I got really annoyed at the fact that other people were writing definitions and I would hover over them and they wouldn't have a doc string. So I dumped a bunch of syntax and environment into which was a very easy thing to do. The Lean community has made everything so easy. The way that happened was I opened an issue saying it would be really nice if PRs would fail continuous integration if the declarations didn't have doc strings. Oh, and if the lines were more than 100 characters, because I have to have my font big because I've been my 50s, my eyesight's going. And instead of wearing glasses, I just put up font size. So over 100 character lines are really long. So I opened an issue, I think a week ago, and then 2 days later, some random drive-by PR said, yeah, done. And I merged these PRs, and now all of a sudden I had issues. And then some other PRs had conflicts, and then I merged main into these other PRs, and then all the PRs started failing because they all had declarations without doc strings. So I was like, this is great. So my code is, as of last week, is suddenly much higher standard. So then once the computer is happy with the code, me and other people review the code, and then it gets. And I'll show you, just to show you what the project page looks like. So on Monday, very conscious of the fact I was giving a talk on Thursday, I had a look and there were no unclaimed tasks at all. So I quickly scrabbled 4 more unclaimed tasks together so I could show you what an unclaimed task looked like. But I did that on Monday and 3 people have claimed the tasks already. So I don't understand. No. It's weird. I don't get Max. Why can't I scroll with 2 fingers? Anyway.
It goes in the other direction.
Okay, so there we go. So there's various. So these are examples of tasks which you can see by the numbers. So I put new sorries in the repository and said these need to be done, and I just dumped them, and then people just randomly claim. And in fact, this one has been claimed as well. Nobody typed the word claim into GitHub, but somebody just DM'd me and said they were going to do it. And in fact, there's a PR. It's actually even done. So, and then you can see, I don't know, there's my pull requests. There's an exciting new pull request. So we've got machines making pull requests as well, updating things. So those have all just been opened by machines. But I have no understanding of half of this stuff. But away from those, there's a bunch of. I had lots of random branches that were not combined, and I've turned them all into work in progress PRs. So this is the one, concrete Hecker operators. This is the definition of T. But then, as I say, I open these tasks on Monday, and I've got a bunch of. So people so the system works. I break it down and say you don't have to know the proof of Fermat's last theorem. All you have to do is understand this simple little puzzle. And then people just literally come out the woodwork. They're not being employed by me. I don't have any staff. The EPSERT money, 50% of it just magically disappears into a hole. I don't understand how this stuff. It's called overheads, and then the other 50% just pays my salary in 5 years. So it works. And as I say, the big selling point of this method is that by the time the random people on the internet see the problem, it's just literally, it's a GitHub repository that you can, download and compile. And then there's one sorry, and your job is to fill in that one sorry. And you can read the proof of the sorry I don't think I ever showed you the blueprint. Did I show the blueprint? I mean, the point of this, that's Carlson. That's not even my project. What am I doing? Talking about other people's projects. Let me just find you the. I'll show you the LaTeX. Where's the blueprint? So you see, this is what I've been writing. This is just mathematics. There's pages and pages about pages and pages and pages of mathematics, just so we can have everything in one place. And then the idea is the point is you don't have to know a proof of Fermat's last theorem to prove lemma 8.3. You just have to have gone to the Cambridge Part 3 local fields course, or whatever, or equivalent in whatever university you're at. So this is sort of the beauty of the system. And as I say, it's working. Whether it will continue to work, I don't know, but at the minute it's working. So people do stuff, and if people do loads of stuff, then I send them a thank you postcard. So I've sent a few of these already. So if you want a thank you postcard, go complete my task. Apart from that, there's currently only one unclaimed task, and even that unclaimed task has been claimed. So I clearly need to make some more tasks. So there's that. But the big problem I have with my blueprint is that my blueprint is incoherent because I'm writing the LaTeX on the fly, and it's sort of it's disconnected because there's lots of little projects going on, all of which have got nothing to do with each other at the minute, and they're all going to be joined together later. And so the graph looks completely unwieldy and kind of awful. Like it would mostly stay the same, but we'd just be working on one little bit, and you couldn't really. You would go to the blueprint, and your first thought was, "Where's the bit that we're working on?" Because you can't even find it, because there's just like hundreds of nodes, all of which are the same color as last week, and all of which will be the same color in a year's time or a month's time. But then there's just one part which is quite active. So this really wasn't somehow, the blueprint software somehow wasn't a good fit for the project, I thought. And as I say, you would change it a little. So you would find the small connected component, which was actually the mini project we'd be working on, and then you'll do one bit of it, and then you'll recompile, and then it would just be gone. And it's a jump to it, just because of the nature of the software we were using to render the graph. It was just like put the component in a completely new place. So that was a sort of complete pain. And then it turned out that instead of having one graph for the entire thing, there was a setting in the blueprint software. It's extremely well written, the blueprint software. You can have one graph per chapter instead. And because I was running the because the mini projects were all, you can see these little mini projects are all sort of different chapters. The mini project we're currently working very hard on is mini project 6. And so there you can look at the graph. So there you see the graph is sort of a finite size. And it's slowly going green. And as I say, when we get to this glorious theorem here, the mini project will be done. So as I say, if you actually looked at the whole thing, there's just like loads of mini projects and loads of other things as well, and it's, you can't even find the bit that, so this is the active part of the project so far. Right, so there we go. So that's that, and then the last, hopefully I've got, oh, this is great. Yeah, so last 20 minutes I'm going to talk about something completely different. I'll talk about why formalize Fermat at all. So there's the personal reasons, which aren't, I mean, they're my reasons for formalizing Fermat, because this is my favorite computer game. I still get up every morning wanting to prove Fermat's last theorem. The novelty is not, my partner's just been away sailing down the Danube for a week with her father. So all Saturday morning, I woke up at 7 o'clock, at like 7:30, I was just out of bed formalizing Fermat's last theorem. It's quite bad, really, but that's kind of where we are at this point. That's why I want to prove Fermat's last theorem, because I love playing this computer game and I find it very, and the same on Sunday. There was like, this is great. She was away for the entire week, and there was just like every day was proving Fermat's last theorem. Apart from today, when it was frantically hoovering the front room and cleaning the toilets, because she's back. She's back. So, and getting this talk finished as well. So other than personal reasons, one might actually ask the more sensible question of whether it actually benefits anyone else other than me. And examples of things it may or may not benefit would be Lean's maths library, the area in general, formalization of mathematics, and then mathematics itself. So I'll dismiss A and B quite quickly, and then I'll tell you about some math. Given that we're in the maths department, I'll tell you some mathematics. So A, in my mind, the answer is very clear cut. What benefits does this bring to Lean's maths library? And the answer is, well, firstly, with stress testing the definitions, we're saying to the definitions, actually, can we use them to prove theorems? Or is it hell? We've at least one definition. I showed you a bunch of code about Adels. One of the consequences of this work has been we've redefined Adels. We have a new definition of Adels in the maths line. It's now slightly more abstract. The topology is defined in a different way. So it stress tests the library's definitions. It makes the library's definitions better. And then, of course, some stuff gets upstream to the library. So it expands the library as well. There's an Lean's maths library, mathlib, has you can search PRs for PRs with the FLT tag, and then you'll see. And there's many PRs have come from ideas of Fermat that have somehow been upstream to the maths library. So as far as I'm concerned, this is great, because not least because the maths library is going in a direction I wanted to go in. Because this is one of the arguments I gave to EPSERG, was that if we can do stuff like this, I'm not formalizing the original proof, I'm formalizing a more modern proof of the theorem. And so we're getting sort of modern number theoretic definitions into Lean and then hopefully into mathlib. So yeah, I'll talk about a random definition that's now in mathlib later, shortly in fact. But then this other thing, before I start talking about mathematics, what does this bring to the general area of formalization of mathematics? And like the answers are now just, there's just dumb answers. It raises the profile of the area. And for me, I've become convinced that this kind of thing is going to play a role in the future of mathematics. And probably many of the people in this room are at least entertaining that idea. Otherwise, you wouldn't come to the formalization seminar. But it really has raised the profile of the area. I mean, there was a spread about the article in some German science magazine. Like 2 months ago, there was an article about the project in Le Monde. It's like this wasn't quite what I was expecting. But you do get you get stuff both in popular science journals and in mainstream media. It's quite surprising. So that's good, I think. And secondly, you get a new data point. I nearly wore that t-shirt. I'll talk about that. It provides a new data. So what can we do? What can we do? We can prove, we can prove the odd order theorem. We can prove, the Kepler conjecture. These are big. It's like great. We can prove Fermat's last theorem. That's the thing that will, or we won't be able to prove. Maybe it will all go wrong. Maybe Lee will run out of steam and it won't work. I think that's unlikely because I wouldn't be doing this if I thought it wasn't up to the task. But we'll just get a new data point for what these systems can do. So I think those are two obvious responses to what's this bringing to formalization of mathematics. And then, of course, one thing that we're not really doing is we're checking the proof is correct. So often formalizations, especially formalizations of computer-assisted proofs, like the four-color theorem, one of the motivations was to check that the proof was actually right. Because really the Apple and Harkin proof was very kind of ropey in retrospect. There were certain very long calculations were done by hand, and there were plenty of mistakes in the original proof. So people have asked me, am I doing it because I think the proof's wrong? And the answer is just the opposite. I'm doing it because I know it's right. Because it's been studied for decades. It's like if the proof was wrong, it would just be, I would look like an idiot. Well, I mean, everyone would look like an idiot. It's like my project would be broken, and then but it's not going to happen. The proof is fine. So that's not the reason we're doing it. And then there's this sort of maybe is this a reason? You can argue. Obviously, me doing this is producing high quality mathematics in the machine readable format, and so it's going to be great for AI. But I don't think that AI in its current form can benefit much from my theorem. That's my guess. Because I haven't seen AI in its current form benefiting from this huge proof of the odd order theorem. I haven't seen AIs proving the classification of finite simple groups on the basis that it's just the kind of mathematics that goes into the odd order theorem, which is already formalized. So we could train on that. If you're an AI believer, maybe you'll see some benefits, but I'm not going to push that argument. But let me talk about potential benefits to mathematics. So what do mathematicians want? What kind of projects do bring benefits to mathematics? And the most obvious thing is that projects that prove new theorems. That's what 90. When I look at who I was competing against getting this excerpt funding, and indeed when I look at me, years ago before I was doing this sort of nonsense, I was saying to EPSA, give me money because I think I can prove new theorems. So that's the kind of thing that the mathematical community is convinced benefits it a lot. And then new insightful conjectures, that's much harder to do, it turns out. Conjectures are quite rare, and especially being recognized for a brilliant conjecture is vanishingly rare. Like Birch and Swindles and Dyer are in some sense most famous for their conjecture, even though they did many great theorems. Somehow the thing that's attached to their name is the conjecture. But really, new insightful conjectures are somehow very, very hard to come by. And then there's new techniques and new abstractions. So those are the kinds of things that mathematicians would like to see. And we're not going to be proving any new theorems because the proof has existed for decades. It's been read very carefully. It's been generalized and simplified. And the thing I'm doing is not gonna. We're not going to find a new theorem, right? That's not the selling point at all. Because and note that one thing, that first thing, proving new theorems, that's where the prizes go, right? that's the people that win the big prize. When you look at the people who are getting Fields medals, it tends to be because they proved a big new theorem. So in some sense, the mathematics community as it currently stands, the biggest benefit as far as it's concerned is when you're proving big new theorems. So we're certainly not going to be doing that. So what are we doing, and is there any chance it'll benefit maths at all? I mean, one thing is true, is that when I got into this game, it changed the way that I read a mathematical proof. And this quite surprised me. I now read mathematics differently, because before Lean, I would just, the key question when I'm reading a paper is do I believe this argument? Like, does it compile in my head? Does this argument work? Once you finish compiling it, your brain has slightly changed, and maybe you have some kind of understanding of it, which is quite difficult to quantify. But that was the key thing. Like, does the argument work? I would try and compile the argument, and if the argument compiles, I would be like, yes, this works. I could go on to the next theorem, and also I would have some kind of understanding of how the argument worked, which is difficult to explain. But now I ask myself another question sometimes, and that other question would be, is this theorem proving the right thing? And that would tend not to be a question I would ask myself before. Are we actually doing the right thing? Is there a different way to think about this? Is there a better way to think about things? Because formalizing forces you to ask that kind of question. And so now I get to read the proof of Fermat's theorem again, 30 years after I first read it, and I'll be thinking about it differently. And so it'll be interesting to see what happens. So now, as I say, I was going to either talk about errors or I was going to talk about new mathematics. And I ran through the talk this morning and I had to delete the errors. So I'm going to tell you about a new abstraction which came out of the project. And it's, so I was doing something technical that I'm not going to explain, but I was defining the key objects in the Langlands philosophy are automorphic forms. And I wanted to find quaternionic automorphic forms. So D is a quaternion algebra over a totally real field F. And then I base change to the adels of F, and I take the units of this topological group. When you type that, like Lean has definitions of quaternion algebras and totally real fields and the adels, and you make that object, and you say it's a topological group. And then, of course, the first thing that Lean says is, well, why is it a topological group? And this is a really weird question, right? So what the question means is, this is an object which is a group, and it's got a topology, and topology means you can talk about continuous functions, and the group means it's got a multiplication and an inverse. And so Lean is saying, why are those things continuous? Multiplication and inverse. Why are they continuous on this complicated mathematical object? And this is a really weird, I knew it was going to ask me that because I've used it before, right? I understand now the way the system works, and I knew this was coming, but it's just such a stupid question. Because, like, how can it not be a topological group, right? If I'd asked my advisor, right? If you ask a mathematician, why is this thing a topological group? It's like how do you make a function that isn't continuous? I mean, you have to try. You have to say, if x is positive, then it's 1, and if x is negative, then it's 0, right? You have to really do something. You have to you have to do something, and nothing like that. All the topology and the multiplication, they're all just defined by Foliot-Knowles algebra, right? So there is absolutely no way that multiplication is not continuous. So that would be a perfectly reasonable response from a mathematician. Like, of course it's continuous, because what could go wrong? But if the mathematician really is the kind like me and sort of knows about details and thinks about things, they can just say, well, actually, I can see a proof of this. You choose a basis of the quaternion algebra, and you rewrite multiplication in terms of matrices, and you use the fact that you can grind out the calculation, and clearly it's possible. You're the kind of person that worries about details like that. You will know how to sort of sit down and start writing down a really grotty proof, a grotty formal correct proof that this multiplication is continuous. So it is sort of possible. It is, there is a proof, but the problem is I don't want to formalize that proof, right? I'm looking at this now thinking, I know that I can just prove it's continuous by just taking the definition apart and taking it apart and taking it apart, and eventually observing, that it's built from many, many, many smaller operations, all of which are continuous. But I don't want to start, but it involves, making choices. Right? This D is a 4-dimensional vector space over F. The first thing you'll have to do is pick a basis. And then the second thing you have to do is just reduce everything to equation. So I didn't really want to do that. So I want to give you an example. So that's a fancy example, but let me step back and just give you a completely, I can abstract this out and give you a completely simple example that everyone in the room can understand. There's nothing to do with quaternion algebras. So we start with the plane R squared. And the great thing about R squared is that vectors in the plane, represented by 2 coordinates A and B, a vector in the plane has got a length, right? You can take the norm of a vector, and by Pythagoras' theorem, the length of that vector is root A squared plus B squared. And of course, the moment you've got a norm, you've got a distance function. The distance between vector V and a vector W is you just look at the difference between V and W, and then you take its norm. The moment you've got a distance on a space, we can start doing sort of basic sort of calculus or, continuous mathematics. We can talk about what it means, the limit of a sequence of points. That's now a meaningful thing because the sequence has to get arbitrarily close to the limit. And we've got this distance function, so there's a notion of closeness. And we can talk about what it means to function from R squared to R to be continuous because they're metric spaces. And now let's go up a level of abstraction. And instead of R squared, let's talk about an abstract 2-dimensional real vector space for me, which is something that when I was an undergraduate, I had no conception of what the difference was between an abstract 2-dimensional real vector space V and R squared. They were the same thing in my head. But here, when you think about what I was doing on the previous slide, there is a difference, right? So first of all, this is an abstract 2-dimensional vector space. We need to choose, we need to orient ourselves. So we can choose a basis, which is 2 special vectors in this vector space. So it could be like that vector and that vector, right? And then of course every single vector, now you've got your basis, every single vector in that vector space can be written as a linear combination of the bases. So I want to go over here, I do like 4 of those and 3 of those, and here I am over here. So a general vector can now be written as A times the first plus B times the second. And now A and B are real numbers. So now we've got numbers. So now we can define the norm of our vector. Now you've chosen this basis. And now we can define the distance function. And we can talk about functions being continuous. And now the problem is we've got this concept now of functions of this vector space V being continuous, but the definitions of the norm and distance depend on the basis. One reason you can tell immediately they must be on the basis was that you didn't have to choose those 2, right? You could just we could have chosen that and that, right? They don't have to be they don't even have to be perpendicular, right? It makes no sense to say they're perpendicular because V is just a vector space. So one reason that these must depend on the base. The way you choose a basis in a 2-dimensional vector space is you choose any non-zero vector. And that's going to be the x-coordinate, the x-axis. And then you choose any vector that's not on that line, and that's your y-axis. So we've chosen this E and F. So E I can write as a linear combination of E and F. It's 1 times E plus 0 times F, and 1 squared out of 0 squared is 1. And so the norm of E is 1. So you choose your basis, and now your basis vectors are doomed to have norm 1. So of course, if we now double our basis vectors, there's still a basis. But now these new things have got norm 1, and so the distances must be different. So indeed, all the distances are halved. But if you scale one of them and don't scale the other one, then some of the distances stay the same. If you don't change E, then things on the E line are still at the same length, but things on the F line have changed by a factor of 2, and things that aren't on either line have changed by some factor between 1 and 2 that sort of depends on where they are. So the claim is, the claim, which is, you all sort of know, but the claim is that whatever choice of basis you make, you get different norms and different distance functions, but I claim that they give you the same concept of continuity. Right? Whether or not the sequence of vectors tends to another vector, it doesn't matter which basis you chose, even though the numbers you get are different, you get the same concept of continuity. And so the metric is changing, but the topology is staying the same. And why is this true? Because the moment you choose a basis and then choose another basis for vector space, there's a special change of basis matrix, which you learned about in the first year of the undergraduate curriculum here, You've got your change of basis matrix, and all of your intermediate calculations, there's this random extra matrix that you're multiplying everything by a 2 by 2 matrix. And when you look at the formula for how to multiply 2 by 2 matrices together, the formula involves multiplication and addition of real numbers. And lo and behold, multiplication and addition of real numbers are continuous. And so there's the fully formalized proof, you know. There's a proof that you could formalize that these two topologies are the same. And so now the question is, what should we be doing instead? Because I don't, you know, what's the abstraction? So let's say we've got an abstract topological ring now. So for example, the real numbers or the adels, that was the topological ring in my example. And say that topological ring is acting on an abelian group. So the ring's got a topology and the ring is acting on an abelian group M. And so what does it mean for a ring to act on a module? It means you've got, given an element of a ring and an element of the module, you can get an element of the module. So you've got a function from R cross M to M. So R's got a topology, but M doesn't have a topology. And so there's an M on both sides. So it's sort of funny. And so this is the question. Does M actually get a canonical topology from the action of the reals? So if we could do this, then we wouldn't have to get our hands dirty with all this R squared stuff and choosing bases. Is there some magic way of, you've got, the ring has got a topology and it's acting on the module, does the module inherit some kind of magic topology from the action? And as I say, you can't just, I don't know, it's sort of, you can't just push a topology forwards or pull a topology back because there's an unknown topology on both sides. So that's sort of the question is sort of not, it's also not a well-defined question, right? The word canonical is meaningless. Mathematicians would use it, but the question isn't well-defined. This is one of these questions. You'll know the right answer when you find it. This is what the question is. So what kind of, what do we want from this topology? So we've got R as a ring, the ring's got a topology, and the ring is acting on modules. And now, can we put topologies on the modules with the following properties? Firstly, the ring acts on itself. Every ring is a module, like the reals are a one-dimensional real vector space. And so I definitely want the topology, the magic topology that I'm dreaming of. I want that topology to be the topology we started with for the real. I don't want to start messing with the topology on the reals. I want the topology to be well behaved under products, binary products, because product of two modules is a module, and product of two topological spaces has the product topology. And this is the real magic thing. I want all linear maps to magically be continuous, right? That's the thing, because that's the thing I want. I had to prove that some map was continuous. I want to prove that it's linear and so it's continuous. All maps are magically continuous, and all bilinear maps as well, because multiplication is not a linear map, it's a bilinear map. So can we have a topology on every R module with these properties? And the answer is no. I asked this on Math Overflow, and the answer is no, which is kind of annoying. But then I realized that actually in my application for the bilinear maps, I didn't need crazy, I mean, maybe this is obviously a bit too much because anyone who's done infinite dimensional vector spaces will know perfectly well there are plenty of sensible topological infinite dimensional vector spaces and plenty of completely reasonable linear maps which are not continuous. So maybe this is asking too much, but actually, if we just tone down the bilinear map question just to modules which are finally generated, that it turns out such a topology exists. And I had no idea that every module has a magic topology, and under certain finiteness conditions, this magic topology has lots of really good properties, like maps are magically continuous. So that's the theorem we proved. Is it unique? I don't know. And here's some corollaries. I should say that. So if R is a commutative topological ring, like the real numbers, or the adels in my application, and A is an R algebra which is finally generated, an R algebra which isn't too crazy, then you give A this magic topology that's come out of nowhere, and I claim that it's automatically a topological ring. Addition and multiplication just automatically continuous because of the machine. So for example, this would give us a proof that the quaternions, right, the standard classical quaternions, they're a topological ring. And imagine how you would prove that. You would somehow imagine we've got formulae for the multiplication, and you would give it the product topology, and you would write down the formulae and check that it just involves addition and multiplication. But what you don't have to do that. It's just magic. And another consequence, of course, was my group here is automatically a topological group. the machine just proves this now, because without the units of a topological ring are a topological group, and that's a topological ring because it's finitely generated over this vastly non-Theorem complicated topological ring. So we get it all for free. And it's great. You see, somehow there is in the middle of the proof, there's some reduce everything to matrices calculation, but you only have to do it once. And then you get all this stuff for free. And maybe I'll just say what the definition of the topology is, because it's time to wind up. This is how you know that you've got it right, because the definition I'm going to give you is so obviously canonical. So before I give you the definition, I'm going to tell you one thing. Let R be a topological ring. And let's say we've got an R module with a topology. Then that topology, I'm going to say a topological module is a module with a topology, and all the maps that you look at, all the obvious maps are going to be continuous, right? That's what a topological module is. And the big problem, which comes back to your question, the big problem is that given a topological ring and a random module, there's more than one topology that makes it a topological module. So a completely dumb example would be, for R squared, there's the natural topology, the product topology, but there's also the indiscrete topology that makes it into a topological module. Because the target is M. And so there's not one topology that makes it work, which is why the question was hard and interesting. But there's a concept of a topological module. And so given a topological module, you can forget the topology and you get a module. And that's a functor. And so the functor's got some adjoints. It's got a left adjoint and a right adjoint. And one of the adjoints is give every module the indiscrete topology. And the other adjoint is give every module a really interesting looking topology that we can go and experiment with. And then you try and do the calculation for R squared, and it turns out you get the correct topology. So that's kind of good. So there you go. So that came out of just me not wanting to do a grimy formalization. And I've asked about it, and nobody can find it in the literature. But I needed it, so I made it, and I PR'd it to Mathlib. So now the only reference for it is Math Overflow posts sketching the details, and Lean's maths library, which contains a complete API plus lots of proofs. And of course, it looks really nice, like the proofs are all really slick and things like that. But trying to get them all in the right order, you know what formalization is like. You had to get them all in exactly the right order. And you know, it was you don't see the pain that I went through trying to make the presentation look incredibly beautiful. But it's new mathematics that came out of the project, so that was surprising to me. But you know, I don't quite know what to do with it. But we've used it not just in that one example, we've used it in several examples. We've used it for Adels now as well. It has a surprising application for the Adels. And so it's a technique to make formalization easier. So like, do you need to actually construct the adjunction by hand, or does it exist by? No, I have a formula for it. But yeah, but it's a kind of a cool thing. I don't know what to do with it. Should I publish it? I mean, my instinct is too easy. But whenever you work out something, it's always easy when you float it out. So that's it. Thank you very much. Hello.
Thank you for the great talk. I am not a mathematician. I'm one of those problematic computer scientists. And I will ask a question about this thing you say that we say, which is, okay, so you're not, so maybe you are covering this to check if it's not actually correct, because you didn't do the part of the talk about errors, right?
Yeah.
And that makes me think, if there are errors, how do you know one of them is wrong? I mean, I know it's like a matter of belief that, like, I believe it's here, you know, it's true. So, like, wherever error you can search,
Math society has checked it.
Okay.
It's sufficiently. There's errors in the unimportant papers, but the important papers get checked by sufficiently many people.
Okay.
And it's really old. It's been generalized and simplified. Okay. People really deeply understand the proof.
So there's sufficient paper that, I mean, even if the original papers did have errors and someone corrected them at some point.
Yeah, I mean, the original paper did have an error.
Yeah.
But it was never released. It was found by one of the referees.